pleased to introduce the speaker for this session, Anil Nanduri. Anil is Vice President, Strategy and Markets in the Supercompute Group at Intel Corporation. Anil initially joined Intel in 1997 as a chipset design engineer and has since held many roles contributing to the success of several Intel platforms. He received his bachelor's degree in electrical and electronics engineering from the College of Engineering, Trivandrum in India, and his master's degree in electrical engineering from Pennsylvania State University. It will now be our pleasure to hear from Anil Nanduri.
From weather forecasting to human genome mapping, from curing the world's deadliest diseases to designing more energy-efficient materials, high-performance computing touches every part of our lives. The industry and world nations recognize the strategic importance for HPC and AI to drive competitiveness, progress, and security, bringing scientific computing demand to new heights. Hi, I'm Anil Nanduri, and I'm honored to represent the thousands of engineers who are working on our HPC and AI products. Our group's mission, much like the HPC community, is to help solve the world's most challenging problems faster, and to do it in a sustainable manner by achieving results while using less energy. It's a lofty goal that requires us to push the limits of technology and our innovation. Regardless of the obstacles we face, we are always striving to do better. HPC and AI workloads are not only running in the most demanding supercomputers of the world, but more and more customers are now running HPC workloads in the cloud. There's an incredible diversity in traditional HPC codes, and these continue to evolve and advance with the integration of AI-based techniques. If you look at the common workloads by vertical and characteristics, you will see some are memory-bound, others are compute-bound. Some have small kernels with a lot of control flow, others have large data parallel kernels, and most require extremely large sets of data. There is no one-size-fits-all solution. And just like multiple routes to reach the summit of a mountain, the industry has approached this diversity with multiple architectural routes. Route number 1 increases CPU core count, enhances those cores with new instructions and integrated acceleration engines. This enables high reuse of existing code and leverages large system memory. Route number 2 utilizes discrete GPUs to offload data parallel kernels. This leverages the data parallel compute on the GPU with the attached high bandwidth memory. Is the CPU or the GPU route the best one? Yes, but each route has its own pitfalls. Over the last decade, peak compute has increased along the CPU route significantly, multiple times. But the workload performance hasn't kept up because we haven't been feeding the cores efficiently with data. This imbalance has been a major obstacle leading to wasted cycles, wasted energy, and wasted costs. This is like building muscle strength to get to the top of a mountain, but not improving your cardiovascular system to supply that muscle with oxygen. Along the GPU route, we've had to deal with the substantial obstacles of porting and refactoring code. This has been further hampered by proprietary GPU programming environments that prohibit portability between GPU vendors and inconsistency between CPU and GPU implementations. Fundamentally, CPUs have been stuck with too little memory bandwidth, while GPUs have too little memory capacity. And moving data between the two results in lost performance and wasted energy from data movement overhead. We want GPU-level memory bandwidth at scale for the majority of HPC codes that run on CPUs today, while also making it easy to share code investment between CPU and GPU for the workloads, to ensure no HPC workload is left behind. We need a solution that maximizes bandwidth, maximizes compute, maximizes developer productivity, and ultimately maximizes impact. That's why we at Intel are excited today to introduce the Max Series product family. This includes the Intel Xeon CPU Max Series that supercharges the Xeon architecture with high bandwidth memory, and also the Intel Data Center GPU Max series, that is our highest performing, highest density, general purpose discrete compute accelerator. The entire Max series family of products are unified by one API for a common, open programming model to unleash productivity and performance. Let's dive into what makes the Max series products amazing. Xeon has been the foundation for HPC deployments with billions of lines of optimized code. Xeon Max integrates high bandwidth memory to the 4th Gen Xeon scalable processors, codenamed Sapphire Rapids, that's now in production. Xeon Max includes up to 56 performance cores constructed of 4 tiles. The tiles are connected together using Intel's EMIB technology, which is a low latency interconnect that provides full mesh bandwidth. Xeon Max also includes PCI Express 5.0 and CXL 1.1 I/O. The Xeon Max CPU is the first and only x86 processor that supports high bandwidth memory. With 4 stacks of HBM2E and 64 gigabytes of ultra-high band memory in package memory, the performance implications for memory-bound applications are truly astounding. Each tile is connected to a dedicated stack of 16 gigabytes of HBM memory. At the highest core count, this means that the Xeon Max CPU provides 1.14 gigabyte of HBM capacity per core, enough capacity to fit a large percentage of most popular workloads. The Xeon CPU is designed to be used in 3 different memory configurations: the HBM-only mode, or HBM flat mode, or a cache mode. HBM and cache modes can be run seamlessly with no code changes. The choice of HBM-only, flat, and cache is made at boot time. Power is a major limiter for large data center deployments, especially now. So it's critically important that we develop high-performing hardware within the same power and thermal budgets. A Xeon Max configuration without DIMMs, in fact, consumes 68% less power than an equivalent performing competitive Milan X system. Let's look at some of our benchmarks. First, industry standard benchmarks. We show over 5x generational gains and versus competition. If we look at real-world workloads, we have gains ranging from 60% improvement to over 300% improvement. Let me just pause there for a minute. Up to 300% improvement over competition, and significant performance gains when we compare it to our prior generation 3rd Gen Xeon scalable processors. Now let's dive into a few specific verticals and see the impact of the Max series CPU. Manufacturers use HPC and AI at nearly every stage of product development, from design to automation to visualization. Molecular dynamics is a key domain for HPC practitioners. High accuracy computational methods, such as density functional theory, can be very expensive and impractical. To alleviate this, researchers are applying deep learning in conjunction with compute-bound applications such as LAMPS to reduce the time to solution while maintaining the same or similar accuracy. DeepMD is one of deep learning workload that we enable on Xeon Max. With 3 times the training power and 135 times the inference speeds, we can accelerate the time to solution for molecular dynamics. It is 2.9x compared to competition and 3x against our prior 3rd generation. To see it in action, let's hand it over to Chuck in our labs.
MD researchers are applying deep learning in conjunction with compute-bound applications such as LAMPS to reduce the time to solution while maintaining the same or similar accuracy. DeepMD is one such deep learning workload that we enable on our next generation Intel Xeon CPU Max series. The model training can be completed within a minute with a 3x speedup over the previous generation processors. The DeepMD trained model applied to inference with LAMPS can complete a nanosecond scale simulation within 1 hour and provide similar accuracy to DFT computations. This represents a speedup of up to 135 times over some of the most accurate MD potential models commonly used today. With 3 times the training power and 135 times the inference speed, the Max series CPU has the potential to accelerate time to solution across the life and materials science fields.
Another great test for the Xeon Max CPU is Earth system modeling. Because the Earth is big, especially when you split it into small meshes and compare complex physics at every point. A model for prediction across scales, or MPAS-A, is a climate modeling framework developed by Los Alamos National Labs and NCAR. At 60-kilometer resolution, MPAS-A running on Xeon Max with HBM memory is significantly faster compared to Milan X CPU with traditional DDR memory. You can get this performance out of the box without any code changes. Now let's see it in action.
Predictions of weather and climate extreme events rely on sophisticated numerical models running on HPC systems. In this demo, we show how the Xeon Max CPU dramatically improves the simulation speed of the Model for Prediction Across Scales, or MPAS-A, a real-world application used for climate and weather research. We run MPAS-A at a 60-kilometer resolution on Xeon Max and AMD Milan X CPUs. As we can see, the Xeon Max CPU with high bandwidth memory is 2.3 times faster compared to the Milan X CPU with traditional DDR memory. Looking at the memory bandwidth utilization graph, we see the key performance driver in MPAS-A is the total memory bandwidth, where the Xeon Max CPU with high bandwidth memory is the unquestioned leader. In addition, MPAS-A simulations fit completely into high bandwidth memory only and don't require DDR memory, which can help achieve the most cost-efficient solution and energy reductions compared to CPUs with traditional DDR memory. The Intel Xeon Max series processor helps to address the memory bandwidth bottleneck and achieve a new level of performance for critical applications such as MPAS-A.
I'm pleased to say that we have 30 system designs with Xeon Max series CPU from industry-leading solution providers. And we are just getting started. The official launch of the Xeon Max CPU is on the horizon, so watch out for more details over the next few months. Intel is committed to open platforms and industry-defining standards. Customers can't afford to be locked into a single vendor or compute architecture. To help our customers solve their most challenging problems, we must address this entire range of architectures and make them work seamlessly together. We talked about how our open software stack lets you move between architectures with no code changing, saving you both time and money. Let's look at how we do that. One API is an open, standards-based, unifying program model that lets you compute across heterogeneous computing environments, all with a single code base and software stack. Intel started One API and is now a thriving ecosystem. There are 29 One API centers of excellence. The core language and libraries are available across a variety of architectures, with toolkits for domain-specific optimization and Cyclomatic for rapid portability. One API is a central piece of how we see the community evolving and adapting to heterogeneity. I've talked about how we've enhanced the CPU route for the HPC workloads with Xeon Max. We have made similar improvements on the GPU side to address workloads with dense vector and matrix compute. For that, we present the Intel Data Center GPU Max series. The first version of the Max series GPU product line, codenamed Ponte Vecchio, packs over 100 billion transistors into a package and contains up to 128 Xe HPC cores, Intel's foundational GPU compute building block. The Xe-Link high-speed coherent unified fabric offers flexibility to any form factor to enable scale-up and scale-out. We've been talking about the importance of memory and memory bandwidth. The Max series GPU offers up to 128 gigabytes of high bandwidth memory, up to 408 megabytes of L2 based on discrete SRAM technology, codenamed Rambo cache. Rambo stands for Random Access Memory Bandwidth Optimized, and 64 megabytes of L1 cache. The attention to detail in ensuring high capacity and high bandwidth memory hierarchy is all in service of delivering realized workload performance. Beyond memory, another great feature of the Max series GPU is the Xe matrix extensions. Each XMX engine is built with deep systolic arrays, enabling vector and matrix capabilities in a single device. You can get up to 256 int8 operations per clock, speeding AI training and inference. Earlier, we showed visualizations of atmospheric modeling and fluid dynamics. Science is about more than just calculating results. It requires visualization to iterate, learn, and improve. When simulations are run on the GPU, you want to visualize the results there as well. That's why we incorporated up to 128 ray tracing units into each Max series GPU, which makes it a premier product for scientific visualization and high-performance animation, as you can see. Our engineers and partners have been busy porting codes from proprietary GPU implementations to the Max series GPU. Through one API, these ports will serve the entire HPC community regardless of what architecture or vendor you use. And one API streamlines the process to bring CPU implementations that can take advantage of the entire system compute across CPU and GPU. Here are dozens of codes that are running well on the Max series GPU. We continue to tune performance with a focus on productive offload. Let's look at a few examples of how the software effort helps unleash performance. OpenMC is a community-developed Monte Carlo particle transport code for exascale computations. With the Max series GPU, we sustained 999,000 particles per second using OpenMP target offload. This is a 2x performance gain over NVIDIA's A100. NeckRS is an open-source Navier-Stokes solver based on the spectral element method targeting classical processors and accelerators like GPUs. The Max series with SYCL implementations saw significant performance over the A100. Another workload application, RiskFuel, training credit options pricing models, more than 2x faster than A100. We'll be offering the Max series GPU in several form factors to address different customer needs. The Max series 1100 is a 300-watt double-wide PCIe card with 56 Xe cores and 48 GB of HBM2E memory. Multiple cards can be connected via Xe-Link bridges. This is a perfect solution for individual developers to harness the power of Max GPUs in mainstream servers and workstations. The Max GPU 1350 is a 450-watt OEM module with 112 Xe cores and 96 GB of HBM. The Max GPU 1550 is our maximum performance 600-watt OEM module with 128 Xe cores and 128 GB of HBM. These variants address high-density systems with liquid cooling infrastructure. Beyond the individual cards and modules, we will offer modular subsystems with by4 GPU OEM carrier board with Xe-Links built in to enable high-performance multi-GPU communication within the subsystem. The by4 subsystem supports both the 450-watt and the 600-watt SKUs with 512 GB of HBM2E, giving us an amazing bandwidth of up to 12.8 terabytes per second. We have more than 15 system designs from industry-leading customers that will deploy in 2023. So you heard from us about our Max series CPU and our Max series GPU. This Max series product family provides you with a complete platform solution. All the performance results you've seen for the Max GPU were with Xeon as a host. Let's take a look at the benefit provided by combining the Max CPU and the Max GPU. Performance for the classical molecular dynamics code labs running the liquid crystal workload is baselined on the top-end Milan X CPU. We see substantial gains on both third and fourth generation Xeon Scalable processors in two-socket configurations with DDR. Xeon Max with HBM delivers another significant jump. And then we add 6 Max GPUs on the node, and we see almost a 10x leap. You can truly maximize performance with the Intel Max Series product family. The Intel Max Series and the long road to get here signals Intel's dedication to the HPC and AI market. Since we want to keep climbing the performance hill, I'd like to share some updates to our multi-year Max Series roadmap. Rialto Bridge is the next product in the GPU line, also available in PCIe card, OAM, and subsystem form factors. Rialto Bridge will support up to 160 Xe cores and an 800-watt OAM 2.0 module. After Rialto Bridge, we will bring to you a revolutionary architecture codenamed Falcon Shores. This will represent the convergence of CPU and GPU routes to address our obstacles related to sharing and moving data between architectures. Falcon Shores XPU will bring x86 and Xe GPU acceleration together. We expect Falcon Shores to deliver significant performance per watt, compute density, and memory capacity and bandwidth, all in a single socket with a vastly simplified GPU programming model. Products like Falcon Shores will accelerate the convergence of HPC and AI and also bring greater energy efficiency and sustainability to the data center. The Falcon Shores architecture also enables flexibility to integrate new IP both from Intel and you while leveraging the Intel IDM 2.0 model. This is the journey we are embarking on. Customers are asking for this, and we need to build an architecture and deployment to enable the future of HPC. A general-purpose solution is good, but not sufficient. As more customizations are required, Falcon Shores will serve as a foundational architecture for customer solutions at scale with a rapid deployment cadence. We've covered a lot of ground today. It's been a long journey with many obstacles that we had to jointly overcome. As we continue to push the envelope, I want to thank the industry for your partnership and for pushing us to new heights. The Max Series product line of CPUs and GPUs and One API are ready for your most demanding HPC and AI codes. Looking forward to seeing how you will use these products to realize our shared goal of solving the world's most challenging problems faster. Thank you.